All right, in this video we're going to take a look at rotational kinetic energy. So what we learned first semester is that objects or rigid bodies, objects that don't change shape or form, that move through space have kinetic energy. And we've said that and derived that kinetic energy is related to the object's mass and how fast they're moving, their velocity squared. So that's independent of direction, but any moving object with a mass and a velocity has some kinetic energy. Now, we're going to call that translational kinetic energy because really this is the overall energy an object has due to the motion of the average position of its particles. And the average position of its particles is the center of mass of that object. So I take a ball, I throw it through the air, that center of mass moves, that center of mass has an average velocity, and 1/2 mv squared will tell me how much kinetic energy that object has through its motion through space, the motion of its center of mass through space. But there are some types of motion that don't involve motion of the center of mass. And so we have to account for kinetic energy nonetheless. So let me give you an example. Let's take a fan that has 4 blades. So the center of mass of that fan is the center of the fan if the mass is equally distributed around. But let's say I were a particle on the blade near the end and the fan began to rotate. Well, that particle is going to gain speed, and it's going to have a certain velocity as it moves through space, even though the fan overall is not moving through space with any translational kinetic energy. So we have to account for this kinetic energy differently, and so we call this rotational kinetic energy. And it's very similar to translational. So if k sub t is 1/2 times the mass times the velocity squared, k sub r is 1/2 times the equivalent of mass in the rotational reference frame, which is moment of inertia, and the equivalent of velocity in the rotation reference frame, which is angular velocity. So 1/2 I omega squared. So for objects that are just rotating without their center of mass moving, this is how I can find the kinetic energy due to that rotation and the subsequent motion of the particles. So k trans, k rot, sometimes this is just k sub r like I've used, sometimes this is just k sub t. But any object can have both. Now, when that's true and the center of mass is moving through space and rotating at the same time, we can say we have both. So an example of this would be a bike tire. So a bike tire that has spokes begins to rotate, and because of the force of friction between the tire and the road, there is a translational motion through space. So the center of mass of the bike moves with some velocity, but the bike also rotates at some omega. So I'm going to have both. The overall kinetic energy will be a combination of the two. Okay, so one thing to note about this rotational kinetic energy is that it is also a form of mechanical energy, and it's conserved under the same conditions that we saw first semester. So our EQ goose now has an EQ goose k or ker, right? EQ goose, this being translational, this being rotational kinetic energy. So it's a conserved form of mechanical energy, just the same. All right, now let's look at a couple of examples on whether objects have translational kinetic energy, rotational kinetic energy, neither or both. So a bicycle traveling at a constant speed. Well, that constant speed means the bike actually, as it rides, will move through space with some velocity. But we also know the tires are rotating with some omega. So we say the bike would have both kt based upon the motion of its center of mass and k sub r based upon the rotation of its tires. The blade on a box fan as it's turned on high. Well, this one was an example I used earlier where we have a rotation but not a translation of the center of mass. So this would just be a rotational kinetic energy due to the spinning of the fan blades. A wheel of cheese sliding down a ramp. So sliding means not rotating. Therefore, I would say this block of cheese has translational kinetic energy, as it's an object, a rigid body, where the center of mass is moving with some velocity through space. And then could be accelerating and increasing its KE as it moves as well. A basketball on its way towards the hoop. Now, I guess it depends on how good of a shot you are, but most basketballs, when they're shot, are given a backspin and a rotation. So if that's the case, I have some K rotational due to the backspin of the ball, but the center of mass is also moving through space. So I have some K translational from the motion of the center of mass. So in that case, I would have both. A perfect knuckleball. Well, those of you baseball fans out there should know that a knuckleball is a ball that's thrown intentionally with no rotation. Okay. And because of that, it's subject to the differences in air pressure and some of the differences in the way that the air resistance acts on the ball as it travels through the air, causing it to move in different ways. You can't predict its motion as easily. So no rotation, but translation through space. Therefore, it has K sub T. A stationary windmill, again, very similar to the box of a blade, or the blade of a box fan, So here's your windmill, and it has its windmill blades, and those are rotating around clockwise or counterclockwise, however that's set up, but the center of mass is not moving, so it has K rotation. So brief summary. An object can have both translational kinetic energy and rotational kinetic energy, or either. They're both forms of mechanical energy. I can find the rotational kinetic energy by taking 1/2 I omega squared of the object, and if I have both, I just add the two kinetic energies together to get the total.